Now, it didn't tell us what the initial and terminal point is, but we can figure it out just by the directed line segment. It always starts with the initial to the terminal point. So we know that Q is the terminal point here. Okay, so we know our position vector, which is what we have to find first. That's equal to our directed line segment, which is equal to our terminal point minus our initial point. Okay, so that's going to equal our terminal point, which is Q. So that's 7, negative 16. So we have 7, negative 16 minus negative 3, negative 6. Okay. So we have 7 minus negative 3. Oh, sorry about that. Should be a comma there since we're combining the two vectors. You have negative 16 minus negative 6. Okay, which gives us 7 minus negative 3 is 10. 16 plus negative 16, or plus positive 6, I don't know why I said 16, is negative 10. And actually that's just coincidence that they're opposites, or they're the same. They don't always appear that way. Okay, so this is our position vector. Okay, now once you have your position vector, now you can find your direction and magnitude. Okay, so next we find our direction. So the direction of our vector, remember that's the square root of the first component plus, well, first component squared and the second component squared. Okay, which equals the square root of 10 squared plus negative 10 squared, which is the square root of 100 plus 100, which just becomes the square root of 200, which is equal to the square root, well, 10 times the square root of 2. So our direction is 10 square root of 2. I mean, not direction, magnitude, sorry about that. I was thinking ahead to the next step already. Okay, now we go to the direction. Okay, so we know for our direction, it's theta is equal to tangent inverse of the second component divided by the first component. Okay, so that means our theta is equal to, our first component is 10, and our second component is negative 10, so it's negative 10 over 10, which means our theta is equal to tangent inverse of negative 1. Okay, so if we apply tangent to both sides, we have tangent of theta. The tangent and tangent inverse here would cancel out. So we have tangent of theta would equal negative 1. Okay. Now the one thing here is the fact that our 10, negative 10 vector is in quadrant 4. Okay. So we know for a tangent theta to equal negative 1, theta has to equal, well, you could say negative 45 degrees, or theta would equal 315 degrees. Straighten that up a little bit. Okay, which are both in quadrant 4. Okay. So to find that, if you want to just find out how you do that, you just first tangent theta equals 1 when theta is 45 degrees. Okay, so we know it's going to be 45 degrees here for tangent just equal 1. So we know for tangent to equal negative 1, you have to go where it's in quadrant 4. So that's where you have your, I'm trying to think where y is negative. So that would be square root of 2 over 2, comma, negative square root of 2 over 2. Okay, so that's when your theta would be negative 1. And all I did was take it from being negative 45 degrees and then going around another 2 pi, because remember, you just go 2 pi over and over and over again, end up right in the same spot. So negative 45 degrees plus 360 degrees brought us right at 315 degrees. All right, so any questions on that one? All right. Okay, so next, this is more about notation than changing anything up. Oh, anyone's still writing? No, okay. Position vectors are sometimes written in terms of an I vector and j vector. Now in the book and on the homework, they won't have the little arrow over them. They'll just have it in bold print. So when you see the bold print, then you know that's your vector. But since we can't do bold print by hand, we just put the arrow over it. Okay. So for example, if you have the vector v is equal to 4, 9, then we can rewrite that as 4i, make my little arrow, plus 9j. So it's just different terminology. So if we drew that on a graph, and we know we have the vector at point, 4, 9, then that means from this point to this point would be 4 times the I vector. And from this point to this point would be 9 times the j vector. From this point to this point would just be your 4i plus 9j. So any questions on that one? Okay, so let's say, for example, if we're given point A is -3, 1, and point B is 5, -6. Say we express the line segment from A to B, or directed line segment, in terms of I and J. Okay. So first thing we want is our position vector. Can't do anything without that. So our line segment from A to B, so we know that's our initial, our A is initial and our B is our terminal. That's going to equal our position vector, which is your terminal point minus your initial point. Okay. So that's going to equal your terminal point, which is B. So you have 5, -6, minus -3, 1. Okay. So that gives us 5 minus -3, and -6 minus 1. Which gives us the vector of 8, -7. We can convert that to 8i minus 7j. So it's just another way of rewriting the position vector, or any vector for that matter. All right, so any questions on that one? Okay. Anyone still writing? All right. Okay, so let's say if we're given that our u vector is -4, -10, and our v vector is 7, -3. Find our u vector plus v vector, written in a times I plus b times your j vector form. Okay. So really just add those together and convert it into our form using the I and j vectors. Okay, so u, we can make that -4i minus 10j. So we can just rewrite them separately. And our v vector, we can make that 7i minus 3j. So you can wait to the end to convert them, or you can convert them right at the very beginning. Okay, and the reason this helps a lot is because your u vector plus your v vector is just -4i minus 10j plus 7i minus 3j. And you really treat those like you would variables. So if you had -4x plus 7x, that would just be 3x. Same thing here. Negative 4i plus 7i is just 3i. Negative 10j minus 3j is negative 13j. So if you waited to the end to do that, you'd still get the same answer, but sometimes doing it at the beginning helps when you're just adding them together. All right, any questions on that one? Okay. All right, so now we're going to start with the unit vector. Now, if you remember, the unit circle was just a circle whose radius was 1. Have a radius of 1. Unit vectors are pretty much the same, but they have a magnitude of 1. Are vectors with a magnitude of 1. Okay, and they also have the same direction as the vector itself. So the vector that you start with, your unit vector, has the same direction, but just a magnitude of 1. So in order to find the unit vector of v, the vector it's the vector divided by the magnitude of the vector. Okay. Or you can write it as 1 divided by the magnitude of the vector times the vector. And this way is handy because the magnitude of the vector is always a scalar. So if you get that scalar multiplied to the vector, that's a quick solve. Let's say for our first example, if we're given that our W vector has the components 5, -4, find the unit vector. Okay, so we know the unit vector is just going to be the vector itself divided by the magnitude of the vector. Or you can make it 1 over the magnitude times the vector. Okay, so first thing we have to do is find the magnitude. So we know the magnitude of the W vector is going to equal the square roots of its components. We'll call it W1 and W2. So W1 squared plus W2 squared. Okay, so that's going to equal the square root of 5 squared plus -4 squared. Okay, which is the square root of 25 plus 16, which equals the square root of 41. All right, so we know that our magnitude is square root of 41. Highlight there a little bit. Okay, so next we just plug it into our unit circle formula. So we divide the vector by the magnitude. Kind of separate that a little bit. Okay, so we have our vector divided by our magnitude, or you can make it 1 over the magnitude times the vector. And that way is a little easier because that gives you 1 over square root of 41 times the vector 5, -4. And since that's just a scalar, all we have to do is distribute it to both. So our unit vector is 5 over square root of 41, -4 over square root of 41. Okay. You can always double check to see if your unit vector is right. Because remember, a unit vector has a magnitude of 1. So if you check the magnitude of your unit vector, it should equal 1. So your vector, bless you, has a magnitude of 1. So that means the unit vector of 5 over square root of 41, -4 over square root of 41. So we want the magnitude of that. Uh-oh, forgot my other little bracket. Okay. So remember, that's the square root of each component. So we have, not the square root, the square. So you have 5 over square root of 41 squared plus -4 over square root of 41 squared. And that gives us the square root of 25. Square root of 41 squared is just 41. So you have 25 over 41 plus 16 over 41. Uh-oh. Okay. So that gives you square root of 41 over 41, which is 1. Okay. So that's how you know your unit circle is correct. I mean, not unit circle, unit vector. All right. Any questions on that one? All right. I say individually, they're not horrible. There's just so many of them. All right, anyone still writing? Yep, I'll leave it up for a few more seconds. All right. Okay, so let's say we want to rewrite our vector components in terms of magnitude and direction. Okay, so let's say if we go back to our cosine of theta is x over the radius, and our sine of theta is y over our radius. Okay. Now, since we're talking about vectors, our radius is just our magnitude. Okay, so let v equal some components x comma y. So instead of using v1 and v2, I'm just going to use x comma y for this one, just for this example purposes. That means the magnitude of the vector is the square root of x squared plus y squared. Just the square root of the component. The square root of the component squared. Okay? So we know that since we're talking about vectors, our radius is actually just our magnitude. Shows the length of the vector, where the radius shows the length of your hypotenuse. So x equals r cosine of theta, and y equals r sine of theta. We can convert those to x equals the magnitude of your vector times cosine theta, and y equals the magnitude of your vector times sine of theta. Okay, so you can rewrite your vector to equal, instead of x comma y, it can equal the magnitude of the vector cosine of theta and the magnitude of the vector sine of theta. Or if you want to write it in IJ form, the magnitude of the vector cosine of theta times I vector plus the magnitude of the vector sine of theta times the j vector. Okay, so those are written in components of magnitude and direction, where you have your magnitude, which is the absolute value looking sign, and you have your direction, which is your theta. All right, so let's say, for example, might as well restart it since it